When we have a limiting reactant problem, reactants are to the left of the arrow. We know we have a limiting reactant problem because we were given two quantities, and we're asked how much of aluminum oxide is being produced. This is like saying I have 2 bike frames and 10 tires. How many bikes am I going to make, right? I'm only going to be able to make 2 bikes no matter what. I could have 1,000,000 tires, but if I only have 2 bike frames, I can only make 2 bikes. So I'm going to have leftover tires. That's what this question is asking down here. Okay, well, you only need 4 tires, so if you had 10 tires, you have 6 left over, okay? So I'm going to do stoichiometry from the aluminum to the aluminum oxide to show that I'm only going to make 2 bikes. And then I'm going to do it again from the oxygen to the aluminum oxide. If I only considered tires, though, and I had 10 tires, and I didn't think about bike frames, it would appear that I could make 5 bikes because I had 10 tires. But I can't actually make 5 bikes. I can only make 2 bikes. This second one is never the answer. Not the second one. The bigger one is never the answer. 5 bikes is never the answer. There will never be 5 bikes with only 2 bike frames. So don't like circle it. Don't add it together. Just like scribble it out. You don't even have to do it all the way once you figure out which one is the smallest. And then this stoichiometry here is like, okay, well, I know my bike frames are going to run out first. So how much of the tires am I actually going to use? So if I'm going to run out of aluminum first, how much oxygen am I taking with it at a ratio of 4 to 3? And it's 4.4. So if I started with 5 and used 4.4, I end up with 0.6, which has wrong sig figs. It should be 0.6, not a 0, left over. Okay. What I'm going to have you do, part of learning is like writing and doing it, but also to help you learn is to say it. So I'm going to turn the music back on. Being recorded, YouTube kicks them out if the song plays for too long for copyright things, so I'll be like switching songs and turning off and on a lot during this hour, so sorry, it's going to be annoying. But I've like recorded a 50-minute lecture and it got removed, and it was like a super important lecture that everybody wanted, and it got removed by YouTube. So I have to be conscious of that. But go ahead and talk about I know I just said it. I know I did, but you're going to say it again. Talk about the different steps and how you knew what to do what, how you came up with all the answers. Ready, go. Okay, can we look at this one? For every unit, I will give you a list of learning objectives. Essentially, if there's 13 learning objectives, that means there's going to be 13 questions on the test. Okay? So, remember I said yesterday, like you can't not learn something. You'll be held accountable for everything that College Board wants to learn for the exam. This is a simplified list of what the College Board has given me. Throughout the year, I think there's 157 of them. These first 13 are basically all summer homework except for number 13. Number 13 I'm going to teach you today. So what I'm going to have you do, these are private documents. This is just a way for you to keep track of like things you need to study. Nothing is ever a surprise. Not a single test question will ever be a surprise for you. You will know that there will be a question on isotopes, okay? Like I'm telling you there will be. So what I'm going to have you do is, this is a working document as well, so we'll revisit this every once in a while, but you're ranking yourself 1 to 10. 1 is like, I have no idea. So your 13 should be a 1. Like, you don't know how to do combustion analysis yet. I have not taught it to you. You've never learned it before. I assume you haven't learned it before, unless you went to a different school. 5 is like, okay, well, now I can do limiting reactants problems with help. I'm good. That's 5. And 10 is like, okay, like, I can name compounds, no problem. I know my help, secondly. So, you do not have to pick 1, 5, 10. You're just like deciding somewhere in between there. You can do an X, you can do a circle. Go ahead and do that for all 13. Sorry, I just, like, YouTube gets mad at me. We have a 3rd grader and 6th grader in TikTok. It's very prevalent in my household. Yeah, she has a TikTok. They like had him in like 1st grade.
It's actually starting to be like
it's like the youngest social media type thing.
I hate
TikTok is trendy now.
everyone that begs for likes or takes like the same video that's already out there.
Yeah, there's like a.
And they just use like songs in the background and not other songs.
Okay, next thing we're gonna do. See if you could get out your lecture notes for today. I gave them to you. They are right. This is the one and only lecture that I will do for summer homework. There's just 3 things I just want to double check that you're good to go on. And then I'm going to teach you something new called combustion analysis. So what I'd like you to do first, if you'll notice, number 1, A and B are identical to your, okay, not word for word, but the same problem as your warm-up. So I want you to do it again, this time with your warm-up right next to you. Like, do not try to do this on your own. We will get to a point, actually, starting now, you cannot do things wrong. We do not have time to unlearn things in here. We only have time to learn them and practice them. So forever and always, you need to have support next to you. You will have a battle buddy. You will have my answers up here. And so starting now, you have a warm-up that's like the same exact thing. Please do not do this one wrong. Do this one perfectly. Number 1, A, B, and C, if you remember, would be awesome. Ready? Go. Percent yield is your actual yield divided by your theoretical yield times 100. So if I actually produce 99.5 grams, like I put it on a scale, it says 99.5. Compared to how much my math says. My math says I should have produced 100 grams. So I have a 99.5% yield, which means I lost 0.5% somewhere in error.
So where did you get that 99.5?
That's it. In the problem.
Oh.
Got it. Okay. Taking your answer and making a comparison. 2 other things I just want to review with you quick. Isotopes. An isotope is an atom that has a different number of neutrons. Okay. okay? So like carbon always has 6 protons. That's what makes it carbon, because it has 6 protons. But there's lots of versions of carbon. Some have 7 neutrons, some have 5 neutrons. For this example, it's talking about chromium. Chromium is number 24. That means it has 24 protons, okay? And this is saying I have a chromium 50. Those are the mass numbers, 52 and 53, okay? So if you remember way back that the mass of an atom is the protons and the neutrons added together. Electrons don't have mass because they're not things, they're waves. Okay, so if it's chromium, my protons is 24. The first one says my mass is 50. I could easily find my number of neutrons. Okay, so with your battle buddy pretty quick, go ahead and find those neutrons. Ready, go. Right?
That's pretty tough.
I know. Wouldn't that be nice? Is that easy? Mass spectrometry. If you watch like crime scene shows, they simulate a mass spectrometer. They take like a sample and they put it in a machine, and then like a printout comes out. It's like, oh, it has carbon, hydrogen in it. That would be this. Mass spectrometry is a way to determine amounts of things that have separated by mass, okay? So they put in a sample of silicone, and it showed that 92% of the sample had a mass of 27.9. 4.7% of the sample had a mass of 28.9, and 3% had a mass of 29.9. So when we take a look at silicone on the periodic table, this mass number here is an average atomic mass, but it's not like an even average, it's a weighted average. And they get those weights from the mass spectrometry data, okay? So if we wanted to find the average atomic mass, we would not add up these masses divided by 3. We have to account in the abundance. So I would say 92.21%, 0.9221% of its times of the sample weighed 27.9763. And 4% weighed 28.97649. And 3% weighed 29.9737. And that's called a weighted average, where you take into account the abundance. So I'm going to have you push those buttons in your calculator. I know you know how to push buttons in calculators, but it's important to learning to be active in your learning and to interact with the material. So you're going to go ahead and push some buttons for me. You don't have to. The unit is grams per mole once you push those buttons. It's called a weighted average using the abundance. Okay, let me teach you something new. Things I have to tell you about learning something new. When I lecture and teach you something new that requires multiple steps, or there's like things in there that I want to point out, I do them in color. I change my color. So I typically write black, but then I will move to red, and then I just go in order, green, and then blue. So I have these pens available to you during lecture. They have all the same colors as me. If you would like to follow along color coding with me, you are always welcome to come up and grab them. If you don't like pens, I have pencils. If you have your own things, I will most likely warn you, like, hey, I'm color coding this, and give you a little bit of time to get yourself ready. If you don't care about color coding, don't worry about it. It's just an option for you. The one thing is, I do pay for these with my own money, as much as my husband likes to fund my classroom. They are not cheap, and they tend to walk off. So if you please Try not to steal my stuff, that'd be awesome. So I'm going to turn the music back on. Get ready to learn something new, whatever that means to you. Ready, go. Now go. Now go. Okay, combustion analysis. Combustion means burning. Okay, so we're burning something. And what we're doing is it's a way to find the empirical formula. The empirical formula is the reduced version of a hydrocarbon. Wow. Hydrocarbon is just like it sounds, hydrogen and carbon. Sometimes oxygen, sometimes nitrogen too, but the base is hydrogen and carbon. So what they do is they take a sample and they burn it. This is fire, that's what it's for. Okay, so they burn it, which means they're just reacting it with oxygen. Then they collect a certain amount of water that comes off of it, and then a certain amount of carbon dioxide, because the products of a combustion reaction of a hydrocarbon is always carbon dioxide and water. Okay, so these questions all sound the same. It's all going to be the same information. So it says isopropyl alcohol, which is rubbing alcohol, is composed of carbon, hydrogen, and oxygen. Combustion of 0.255 grams. So in my furnace, I put 0.255 grams of isopropyl alcohol. From that, I produce 0.561 grams of carbon dioxide and 0.306 grams of water. I'm going to determine the empirical formula from that. There's like 2 rounds of calculations to do these empirical combustion analysis problems. First round is just straight stoichiometry. Second round is empirical formula calculation. So I don't know how well you remember that. So I'm going to start step 1. I'm going to do it in black. I'm going to convert my grams of carbon dioxide to just the grams of carbon, because all of my carbon had to turn into carbon dioxide. There's nowhere else for it to go. It's not magic. Okay? So if it says I have 0.5, ooh, if you're a big writer, write little. There's going to be a lot going on. If I have 0.561 grams of carbon dioxide, I need to convert that all the way to just grams of carbon. So the way I do it is I say, okay, grams of carbon dioxide, grams on top means grams on bottom. I'm going to convert that to moles. So the molar mass of carbon dioxide, I'm going to make you push your buttons. I know you know how to push buttons, but it's about being active. 1 carbon, 2 oxygens. Carbon is 12.01. Oxygen is 16. So now I've just converted it to moles of carbon dioxide. Once I'm in moles, I'm switching to red because this is like the stuff that's kind of weird and hard to remember. Once I'm in moles, I'm going to convert from moles of carbon dioxide to just carbon. If I've handed you a carbon dioxide molecule, tell somebody next to you, how many carbons would there be in a carbon dioxide? Ready, set, go. What? So it's like a mole ratio of a molecule, not of like a valence equation. So now I'm at moles of carbon, but I'm trying to get to grams of carbon. Each mole weighs 12.01 grams. So what I did is I said, okay, I have this much carbon dioxide. How much of that just is the carbon? Okay, go ahead and push your buttons. See if you can get an answer. I'm going to do that all over again, but now from water, because my other sample is water, and I'm going to go to hydrogen. Same game, but water to hydrogen. So I have 0.306 grams of water. I'm going to convert that to moles of water. Water is 2 hydrogens. Each is 1.01. Oxygen is 16. The next step is a ratio step. Tell somebody next to you, if I have 1 water molecule, how many hydrogens is that? Tell somebody next to you, where does that go? 2. Okay, so it's not 1 to 1, now it's 1 to 2. I'm at moles of hydrogen. 1 mole of hydrogen is 1.01. Some of you might be going to like, it's diatomic, H2, how come it's not 2.02? It's not diatomic. It's hydrogen. It's a hydrogen atom. If you're worried about this little 2 here, that's why we multiply it by 2 in the math. So I'm taking care of it here. Don't do it twice. Don't be redundant. Otherwise you'll end up with 4.04. Okay, go ahead and push your buttons. Okay, now I know how much carbon, now I know how much hydrogen. I do not yet know how much oxygen, because some of it's wound up in the carbon dioxide and some of it's wound up in the water. So all I'm going to do, this is me writing big, all I'm going to do, step 3, is I know how much the whole sample weighs. And the sample has carbon, hydrogen, and oxygen in it. I now know how many carbon grams I have, and I now know how many hydrogen grams I have, so I can easily get my oxygen. So I think it says in the problem I have 0.255 grams altogether, and I already figured my carbon, and I already figured my hydrogen. The only thing else it can be is oxygen. There's nothing else in there. Hi.
Oh,
I said hi, but I wasn't actually ready. Okay, now I'm ready.
never mind.
Okay, that's round 1. Round 2 is now to figure out the empirical formula, because that's what it wants us to do. This may or may not be fresh in your mind, depending on if or when you did the summer homework. To find the empirical formula, first we have to convert to moles. Got to compare apples to apples. Once we convert them all to moles, we divide each by the smallest to get a ratio that we use as subscripts. So I'm kind of undoing what I just did, but I switched to green to show like a second round. I'm undoing it because I have to do the empirical formula. Okay, so I'm going to go back up to my grams. 0.53 grams of carbon, turn it back into moles. 12.01 grams in 1 mole equals. Hydrogen, turn back into moles. 1.01 equals. Diatomic hydrogen is like when it's by itself, it's in a compound. And then my oxygen that I figured out down here is 16 equals. Go ahead and push your buttons. Find all 3 moles and look for which one is the smallest. Find all 3 moles and look for which one is the smallest. I got 0127, 0346, and 00423. 00423 is the smallest, so we're creating a ratio. I'm going to divide each of them by 00423. Divide by 00423. Divide by 00423. I'm creating a ratio to the smallest to see what those subscripts are. I divided them each by the smallest number of moles. So I divided them each by 0.00423. 3, 8, and 1. Attached to your lecture today is your homework problems. If you flip it over, there are 3 more combustion analysis problems. All answer keys for everything ever are posted on Schoology, so you can check for it there. If you wouldn't mind, before you put things away, please just talk to the person next to you about the steps of what we did. Learning it is many, many layers. Just doing it barely counts as learning. So go ahead and just talk it through. Lisa.